going to speak on the role of computers in statistical research. And for those of you who know nothing about him, I'll give you some of his fantastic credentials. He has 3 doctorate degrees. The first one was earned in math at Berlin University, second one in mathematical statistics at Cambridge, and a third Doctor of Science degree in math statistics at the University of London. He is a fellow of the Institute of Mathematical Statistics, a fellow of the American Statistical Association, a member of the International Statistical Institute, fellow of the Texas Academy of Science, and a fellow of the American Society for Quality Control. In 1973, he earned the Samuel Wilkes Memorial Award in statistics. Currently, he is professor of economics and distinguished professor of statistics, and he's director of the Institute of Statistics at Texas A&M University. He was on the faculty here from 1953 to 1963. With that, I'd like to introduce Dr. Hartley.
Thank you. Thank you, Becky. Thank you, Becky, for this very nice introduction. As you have heard, you can hardly see me, but I'd like you to hear me, so if you will move forward. I talked quite an awful lot today, so it's a very nice pleasure and a great honor to have been invited by the Society Mu Sigma Rho to come and talk to you on the Iowa State campus. As I have said this afternoon, this is like coming back home, because I have been on the faculty of Iowa State for 10 years, and I am seeing a lot of familiar faces around, and it is nice to see friends and interchange experiences with them. A wonderful opportunity, and the pleasure and honor is all mine. I hope that as far as the members of the society are concerned, who've just gone through a magnificent banquet, that they won't find that this is a very dry dessert after the. I am supposed to talk about the impact of computers on statistics. The topic of this talk may be regarded by some to imply something that is undesirable. Computers are, after all, mechanical tools. In spite what we see advertised in glowing colors about these electronic brains, they cannot do anything on their own account. And the human brain has to provide all their thinking. The idea, then, that this mechanical slave should influence the thoughts of scientists may appear to be altogether dangerous and undesirable. After some reflection, we may be inclined to admit that this new tool may have an influence on our methods of computation. However, computational methods are regarded by many scientists as a sort of second-class area, a necessary evil to obtain numerical answers, a trivial matter not worthy of discussion. Characteristic of this attitude is a casual remark of a statistician. Incidentally, Kempe, I am not referring to you. He was apparently bored when a group of fellow statisticians were discussing convenient computational procedures to obtain certain statistical estimates. He remarked that the computational procedure most convenient to him was to proceed to the computing lab and tell them to get on with it. It is true that computers are mechanical tools. As such, they certainly affect the computational aspects of research in science and statistics. However, will they reach the heart and soul of such research work? Will they influence the outlook of statisticians? I think they will. Let us look at an analogy with which many of you will be familiar. Soon after Röntgen discovered X-rays, their clinical potentialities were realized. They became a mechanical tool to help physicians in their diagnosis. But did they influence the outlook on medical treatment? No physician would dispute today that they did. Quite apart from the fact that X-ray therapy is a recognized treatment, the mere fact that X-rays make it easier to diagnose internal anomalies has influenced the clinical outlook fundamentally. The mere fact, then, that high-speed computers can carry out computations much faster influences our evaluation of research projects in statistics and elsewhere in science. In my brief report on this influence, I will confine myself to a few selected aspects, rather than make an unsuccessful attempt to recite them all. The first aspect is what some of you may regard a very trivial one: the quality control and editing of data. The ever-growing number of studies and surveys in the social engineering and life sciences is producing an overwhelming amount of data. A statistical analysis of such information usually consists of the computation of summaries or estimates from such data. For example, we may wish to check on the accuracy of inventory records of an arsenal by a direct sample survey in the warehouses. This will lead to statistical estimates of the actual inventory as opposed to the inventory on record. Again, we may wish to estimate incidence rates of certain diseases for certain communities from data collected in the National Health Interview Survey, so-called HIS. If the task of a computer were confined to the mere doing of sums and percentages, this would be an easy matter, and one on which a high-speed and high-powered computer would probably be wasted. However, as those of you who have had experience with survey data only know too well, it would be reckless to assume that there are no errors in the data. It is therefore of paramount importance that at all stages of data collection and processing, the quality of the data be controlled. One such control is the scrutiny of data for what is called internal consistency. You may no doubt have heard about the famous teenage grandmothers, which turn up occasionally on census questionnaires and are duly eliminated. Here, the inconsistency of the answers. Relation to head of household, answer mother. Age, answer 16, is obviously inconsistent. Very likely the 16 should have been 61. There are other consistencies which are not as obvious. Others that are conceivably correct, such as a son quote, whose age exceeds that of the wife of his father. It's possible. Or indeed, we may have here a case of some embarrassing situation of information retrieval. She may be his stepmother. Until quite recently, such common sense data scrutiny and consequential editing was performed by hosts of clerks. For studies of a more specialized nature, however, inconsistencies can, of course, only be discovered by personnel with the required expert knowledge. For example, in a study involving clinical examinations of cancer of the breast, the classification of stage, that's a clinical term, may have to be checked against the recorded anatomical or histological division codes. Only personnel completely familiar with clinical concepts will, of course, be able to perform a scrutiny of such records. With the advent of high-speed computers, more and more of these functions of data scrutiny are being taken over by these giant machines. For this to be feasible, we must convey to the computer in minute detail the complete logical sequence of the involved check procedure, including all the know-how as to what the expert would be looking for, what errors the expert would be looking for. Moreover, for the computer to deal with cases which may be errors or may be correct data of an unusual nature, the computer must be able to refer to statistical information so that it can gauge a suspect discrepancy against a statistical tolerance. After all such information has been stored in the computer memory, the data from a particular study, survey, or census are passed through the computer for automatic scrutiny. I'd like to intersperse here a simple example of statistical tolerances. If you're interested in controlling the accuracy of height and weight records of school children, say boys, you may have from past data available a distribution of weight records separately for subpopulation of boys of a particular age, say 6, of a particular height range. Those mean values for weight differ, of course, because they're correlated with age and with height. And so a table like that of, say, upper 1% point, that is to say, weight records that would only occur normally for this subgroup in 1% of the cases, can be picked up as possibly suspect, and pulled out for possible scrutiny, human examination, to see whether they are right or whether something has gone wrong. As soon as the computer encounters an inconsistency, it is instructed to either A, record on tape or punched card the details of the suspected inconsistency in the data and list it for human inspection and reconciliation. Or the A would be called the monitoring of data. Or B, immediately proceed to correct any inconsistent item with the help of statistical estimation procedures and using the data which it has already accepted. The difference is that in the first case, you pull the data out that are possibly suspect, and the human mind will examine by a follow-up whether the record is wrong or right. In the other case, there is built in an imputation procedure, as it is called, to automatically correct the error. There's no question, there's no investigation. Most organizations, such as the Bureau of the Census, using automatic data scrutiny and editing, employ a judicious combination of these two methods. The first procedure is usually preferred in situations when human eliminations of reconciled inconsistencies are administratively feasible, as it would be with smaller, more specialized studies. The second method, automated imputation of suspect or missing data, is adopted when the merging of a correction tape with the original data tape becomes practically infeasible, as is the case with census operations. With an adequate control on the frequency with which imputations, that is automatic corrections, are made, such a method has in fact been in successful use during the latest population censuses. The so-called hot deck method I was going to explain in a little more detail. Some of you in sample survey and census data analysis will undoubtedly have heard about the so-called hot deck method, which is a streamlined regression method, but very streamlined to estimate the regression estimate of a suspect datum from those data points that are acceptable for that particular unit. Today, the Bureau of the Census uses this hot deck method and similar methods of data editing as an integral part of the tight quality control on data from which its releases are tabulated. It can be said that these data editing activities constitute one of the main uses of the high-speed computers. As a matter of fact, estimate that 95% of the computer time of the Bureau of Census high-speed computers are used for data editing, 5% for tabulating the releases. In other situations, it is regarded necessary to always follow up a suspected error in the data by human inspection. You may rightly say that you do not regard such uses of computers as a breakthrough in research. After all, the computer is merely used for functions that could, with great effort, be performed by other means. Moreover, the computer has to borrow its intelligence from its human programmers. However, we must not underestimate the tremendous speed and accuracy with which the computer scrutinizes data. By freeing trained personnel for more challenging tasks, it enormously enhances the potentialities of a research team engaged in these studies, which involve extensive data analysis. Moreover, it permits the analysis of data which, in an uncontrolled and unedited state, would have been too unreliable for the drawing of inferences. Now to the outlook in this area. With the advent of bigger and faster computers, our systems of automatic quality control of data will become more and more ambitious. Although this will result in more searching error scrutiny, it is clearly impossible to provide a control system that will detect any error, however unusual. Much ingenuity is therefore needed by using the knowledge of experts to guide the computer logic to search for the errors and error patterns most likely to be found in any body of data. This is a very interesting application to combination of mathematics and social science in the future. The mathematical solution of thinking of all combinatorial possibilities of error patterns is an astronomical task of error patterns and is out of the question for in data editing to provide for these. You must therefore make a judicious selection of the patterns based on expert past experience as to what kind of error patterns may arise. And it is a very challenging task to provide such efficient data editing procedures. The next aspect I wish to consider is the analysis of experimental data, impact of computer on experimental work for which statistical analysis is used as a research tool. The techniques most frequently used in this activity are analysis of variance and regression analysis. Many excellent computer systems are now available for performing these computations. Undoubtedly, the availability of computers has increased the capabilities of research teams of having their data analyzed where previously desk computers could only cover the analysis of a fraction of their data. Moreover, computers have more or less eliminated the so-called shortcut analysis, such as analysis of variance based on range in place of mean squares. Such shortcut methods have justified their lower statistical efficiency by their rapid execution on desk computers or by pencil and paper methods. Unfortunately, along with these advantages of computers, there are associated serious pitfalls, of which I wish to discuss two very briefly. The first pitfall: the use of inappropriate canned programs. As statisticians, we find all too frequently that an experimenter takes his data directly to a computer center programmer, usually called an analyst, for a so-called statistical analysis. The programmer pulls a canned statistical program out of his file, and their result extensive machine outputs, most of which are irrelevant to the purpose of the experiment. This deplorable situation can only be avoided through having competent statistical advice, preferably in the design stage and certainly in the analysis stage. Often the statistical analysis appropriate to the purpose of the experiment is not covered by a canned program, and it is appreciated that with time schedule pressures may be necessary to use a canned program which gives at least a relevant basic analysis. For example, it may be decided to use a basic factorial analysis of variance and subsequently pool certain components on a desk computer to produce the appropriate analysis of variance. Example, split plot experiment, which can be basically regarded as an ordinary factorial experiment analysis with three factors: blocks B, main treatments T, and subtreatments S. And if there is a canned factorial analysis available, you can, of course, very quickly produce this analysis of variance table and of all the main effects, B, T, S, two-factor interactions, BT, TS, and BS, and the triple interaction, BST, and then pool them in this appropriate fashion on a desk computer to get the appropriate analysis. So it is quite acceptable sometimes to use as a basic analysis, sometimes that is conveniently available, and then modify it for the particular purpose. Shouldn't be too obstinate in this area. The second pitfall I want to discuss is the loss of contact between experimenter and his data analysis. Here it is argued that in the good old days, when experimenters, quote, did their sums of squares themselves, they were learning, quote, learning a lot about their data. And the computer destroys this intimate contact with the data. Now we must clearly distinguish between performing computations on desk computers as opposed to an intelligent scrutiny of the data, preferably an inspection of error residuals, as they're called. The former, that is to say, computation on desk computers, is to my mind pointless. The latter, the intelligent scrutiny of data, highly desirable. Indeed, I would venture to say that all analysis of variance and regression programs should provide options for both tabulation of all individual error residuals for inspection, as well as a statistical outlier tests on all residuals which flag unusually large residuals in case the experimenter overlooks them. It is very strange that the possibilities of faulty records is clearly recognized in the area of censuses and surveys, and all too often overlooked in the analysis of experimental data. But the intelligent inspection of residuals should not only provide a monitor for faulty records. It should also be used by the experimenter to learn something about his data. Systematic patterns of large error residuals often provide useful pointers for the modification of the models, usually the additive models, that were assumed. For example, the form of the residuals in linear regression may indicate neglected quadratic or higher order terms. So residuals are all positive on one side and they say negative on the other side. You can see that possibly there's a quadratic term that should have been fitted. Systematic patterns of large error residuals often provide useful pointers. A factorial analysis of variance of a response Y, in which the main effects of two quantitative factors, input factors, x1, say the temperature of exposure, and x2, say the time of exposure in a plant, indicate large residuals, where the two main effects are perhaps insignificant, but the interaction is significant, often suggests that the relevant input is not the temperature or the time, but may be the product of time by temperature, which is directly proportional to the total amount of heat put into the process. It's a very simple physical engineering theory that might affect the process Y. And here on this slide, I am showing the pattern of residuals that would be appearing if the product x1 by x2, the total amount of heat put into the system, is the important one. As you might expect, there are two quadrants, this one and this one, where the residuals are positive, both x1, x2 below mean, both x1, x2 above mean, and two of them where they're negative. When you see that, it's almost a certainty that the product might be in. Then you have to see whether the product has a physical, real meaning in this particular body of data. I say here that the product y x1, x2 has got the above residuals but would have significant main effects. But if the product x1, x2 is of importance and some negative main effects are subtracted in the real law, then the main effect altogether might be 0, and this law would form these residuals with 0 main effects and a very highly significant interaction. So here is an example in which the pattern of the residuals is a pointer to modifying models that have been postulated, and not all the situations are as obvious as this one, where the interpretation of the product is so reasonable, namely the total amount of heat that has been put into the system. Now let us turn to an area in which computers are used to solve problems in the theory of statistics. I am talking about the solution of statistical distribution problems by Monte Carlo. Monte Carlo, of course, is a very important method. It is sometimes called simulation, but I will first confine myself to the particular application of Monte Carlo to solve statistical distribution problems. Here is an explanation of the general problem of a distribution of a statistic, and then I will explain it in terms of special case of the chi-squared distribution. X sub I is a random sample of size n from a distribution with a density ordinate fx and this cumulative density frequency of capital Fx, so that capital Fx is the integral of f from the lower end up to x. A statistic is defined as a mathematical function of the x sub I. H is a mathematical function of the sample values. At this stage, we might explain these concepts by this example. X sub I is a random sample of size n from a normal distribution, and h of xi is simply the sum of the squares of these normal variables. Of course, everybody knows some sample of normal variables, x sub I, then form their sums of squares. One such function called chi-squared is then scored. It is tabulated in certain categories on a chi-squared scale, scored on a chi-squared scale, and eventually we get a lot of chi-squared values. We've drawn a lot of samples, and so we have a cumulative histogram of this set of chi-squared values. And if this is repeated a very large number of times, there will eventually result a smooth cumulative histogram, which is then essentially representing the CDF, the cumulative distribution function of the chi-squared. Of course, you all know what this function is. It is essentially the integral of the incomplete gamma. It's the incomplete gamma function, essentially. And I will not bother about showing the mathematical form of the true cumulative distribution. Returning to the general definition then, having defined the statistic as a function of the sample values, the cumulative distribution of this statistic H is defined of the probability or the proportional frequency with which these functions of the sample, little h, are smaller than a specified value, capital H, and is therefore defined by this very simple integral. The joint frequency, the product of the fxi, integrated over the sample space R, and the sample space R is defined as that subspace in the sample space xi for which this function h has a value smaller than capital H. This is the mathematical formulation of the solution of a distribution problem. Now, of course, before the high-speed computers were in the picture, this computation was, integration was performed analytically or, in certain cases, by numerical integration methods, but neither of these methods sometimes gives a practical solution to the problem. So we have to rely on the always available Monte Carlo method, which goes back to the concepts of basic sampling and produces the CDF of this statistic from first principles. You say, well, why didn't we always do this? Let us first say then, it is clear from the description of Monte Carlo procedures that I have given that the principal steps of computing estimates of frequency distributions for the statistic H consists of two steps, namely the generation of the samples xi, and then the computation of the function of the xi, and then the frequency, computation of the frequency distribution. These are the simple numerical steps. And I will very briefly describe the first of these steps, namely the computation of random sample xi from a specified distribution such as normal. Well-known procedure is to generate in the computer so-called uniform variables that is variables that have an equal probability to be distributed between this value 0 and 1, which I have called here u sub I. How are those generated? The computer is asked to generate random digits, such as this, say 5 of them, and then it interprets these random digits as a decimal fraction. Random digit means all digits, 0, 1, up to 9, that have an equal probability to be generated. There are many computer programs that do this. You interpret the random digits, so assembled as a decimal quantity that is got an equal chance to lie between 0 and 1. Let's say we get this one. And then you enter a table of the inverse of the CDF of the parental distribution from which you want to generate from which you want to generate random variables, and you get your xi. So xi is the inverse of the CDF with the ui uniform variable substituted. This is a very favorite method of drawing random samples within the computer. Of course, in the case of a normal, what are these? The xi are what some people call the percentage points of the normal, inverse of the normal integral. And we would have to have a subroutine generating these percentage points. So this is really the only thing that you have to do to solve a distribution problem by Monte Carlo, because the next step of computing the function of the xi is fairly simple. So again, I say, people may ask, why didn't we always do this? Indeed, there are now many dissertations that can't solve the problem analytically and solve the problem by Monte Carlo. Now I turn to a big handicap of Monte Carlo methods, and that is the fact that unfortunately astronomical numbers of samples are required to produce solutions to the problem that are of adequate accuracy. As is well known, a very large number of capital N, that's not the sample size, but number of samples, the number of times you have to compute H, for the statistic H is required in order that the empirical frequencies of the capital N values of H provide even moderately accurate estimates of its cumulative probability distribution. An idea as to the magnitude of the number of samples that are required can be obtained by applying the well-known Kolmogorov-Smirnov theorem, criterion of goodness of fit. This criterion measures the maximum discrepancy dn. Here we have a very small sample, 1, 2, 3, 4, 5, 6, 7. And here we have the cumulative sample CDF going up a step of 1/7 at every sample point. Now suppose we knew for this distribution of H the exact mathematical answer here. The Kolmogorov-Smirnov theorem makes a statement about the maximum difference between the exact CDF and the sample CDF. What is the biggest error? In fact, it states that the probability for this maximum error to be smaller than 1.63, this is some approximate result, I shan't go into this, divided by the square root of the number of samples. For the probability that the maximum error is smaller than that gauge value is equal to 0.99. That is to say, in 99% of Monte Carlo calculation, your maximum discrepancy will indeed be smaller than that amount. Now, of course, this maximum discrepancy, as many of you will know, will usually occur in the middle of the CDF. That's not too bad for Monte Carlo applications because it is there that the largest errors are acceptable, and so dn, although it occurs in the middle of the table, will give you a pretty good idea of how accurate the Monte Carlo is. However, what does this simple statement tell us about the sample size n? If we want an accuracy of a table of the CDF to 3 decimals, then our maximum error is 5 times 10 to the minus 4. We are equating 5 10 to the minus 4 to this quantity, 1.63 divided by square root of n, and solve for n. The answer is over 10 million. Over 10 million of samples are required to get that miserable accuracy of 3 decimals. It's a very, very shocking realization. And It is therefore the Monte Carlists, the people who developed Monte Carlo methods for solving statistical distribution function, have developed methods they call of reducing the sample size. It's a bad expression if you see that. It's really reducing the number of samples that they're concerned with. Methods that have been developed are importance or correction sampling, Kahn and Marshall, multi-stage sampling, Marshall, conditional sampling, Tukey and Trotter, antithetic variables, Hammersley and Morton, use of control variables, Feiler and Hartley, stratified sampling, Ringer and Smith. For details of these methods, you have to go to the literature. May it suffice here to say that with all these methods, sampling can be reduced considerably at no loss of precision, and that the relative merits of these methods depend on the circumstances of the sampling problem and on the gadgetry of the high-speed computer which is available. It is of interest that most of the above sampling reducing methods are closely related to devices which sample surveyors use when sampling life population. That is, stratification, regression estimates, optimum allocations, and the like. Designers of sample surveys have always been concerned with reducing the variance of estimates at constant cost or constant sample size. We may in the future look forward to the further blending of efforts between the sample surveyor and the mathematical Monte Carlist. The effect of Monte Carlo on research in distribution theory, the fact that any distributional problem, whatever its analytic difficulties, can be solved by Monte Carlo, has undoubtedly had a profound effect on the orientation of mathematical researches in this area. Indeed, it has been argued that we do no longer require the mathematically ingenious methods of characteristic functions that some of you may have used, combinatorial techniques, and the like to obtain numerical answers. For such a viewpoint is, however, fallacious. For apart from the large number of samples M that are still required in spite of the reducing methods, Monte Carlo answers usually are required in practically all problems depend on a large number of parameters. The sample size n is one of such parameters. Usually, all parameters involved in the parental CDF, that's our normal, that too, will also affect the CDF of the statistic. And there may be others, such as those describing groupings and truncations in the distribution problem. For example, with a moderate number of 20 levels for each of two parameters in f of x, that's the CDF of the parental distribution, and 20 different sample sizes, moderate number of combination, 20 to the 3, that is to say 8,000 Monte Carlo runs would be required, each based on a large number of samples. That in searching for methods to reduce the computational load, one of the most attractive procedures is to derive an analytic approximation including its dependence on all parameters that are involved, and then perform Monte Carlo computations for key combinations of these parameters to obtain a correction for the analytic approximation with the help of Monte Carlo in key positions of the parameter space. This has been a most effective use of combined approximation analysis. There's a little big area in statistics, approximation analysis, and Monte Carlo. The counterpart to Monte Carlo in the applications of statistics to certain engineering and management problems is the well-known simulation, technique of simulation. Most of you are undoubtedly more familiar with computer simulation techniques than I am, and I will therefore confine myself here to a brief description in 2 examples. The first, one example really, I have no time for the second. The example that I want to discuss is the optimization of a production process by computer simulation. The steps in this procedure, I will depart from the text simply as follows. Step number 1, the building of the model to simulate the production process. For example, we may simulate the production process by a directed network for the completion time of all activities in the production process, including bottlenecks and back loops. Those of you who have done PERT network analysis, this is a network without loops, but it is a similar sort of situation. And here we simulate the production process by assuming a specified distribution of the completion times for all activities involved in the production process. 2, computer implementation of the model. In the case of a PERT network, that would be what we call statistical PERT network analysis. We actually use the computer to generate repeatedly a randomly selected completion time for all activities involved in the production process. 3, this is a very important step. The validation of the model for those parameter levels used in past operations. That plant has been run at certain levels, operating conditions as they are called, and you can measure the output characteristics from the plant as it has been run. You now use the computer to simulate that plant as it was run, and you compare the answers from the simulation and the actual fact. Now, it is not a foolproof test of the model, but it's not a sufficient condition, but assuredly it is a necessary thing that should be carried out. Only if very extensive validations of the model of this kind have been carried out can you face up to use the model for optimization of the process. That means you are now changing the running conditions, changing the parameters, plant conditions, in order to optimize the output. Unless the model has been validated, it is garbage in, garbage out. And this is a very important part of the process that is unfortunately often omitted because of the difficulty of getting data. The fourth is obviously the optimization. This is what this exercise is for. You want to run this process in a better way, increase the output and so forth. And the optimization in this case is done a technique by a technique called mathematical programming. Programming has nothing to do with computer programming used in another form. Linear programming is an important special case. This is the last stage after the model has been validated. Can you optimize? This is the operational research analog to Monte Carlo calculations. Now I come to my last item, and this I consider really the most important impact that computers have on statistical research, or indeed scientific research. And that is the impact on mathematical model building, the process of building mathematical models. Perhaps the most significant impact of computers is in this area. Classical analysis used to insist on the use of mathematical models for which compact mathematical solutions could be found. This generated a tendency on the part of the analysts to restrict their studies to such mathematically tractable models, even at the expense of oversimplifying them in an unrealistic manner. Let me describe these concepts first in terms of an set of examples, and these examples are concerned with time-response relationship. There is